will be what condition will we add to guarantee the non-triviality here of this coherent sequence? So in square, the condition is we want to bound the order type of the club sets. We're not going to do that here. We're going to try something else. For every cofinal subset, there's stationarily many alphas satisfying this particular condition. So try to draw something. What we're doing basically is we're saying that you've got some cofinal, so here's our cardinal kappa. You've got some cofinal subset up to kappa. Usually it'll be a stationary set, but doesn't really matter. And what we want to say is there is some stationary collection of ordinals, but this other stationary set consists of points that are not necessarily in B. So this was our set B. We're going to have another stationary set of points that are not necessarily points in B, but points such that when you stop here, the C, let's say call this alpha, the C alpha consists of many points from this beta, from this set B. And so the C alpha here, in particular the non-accumulation points of C alpha, there should be many of them, in fact, enough to get us all the way up to alpha coming from that come from this set B as well. So we'll see as we use it later how it works and why it makes sense to use this. One of the important things about this is that we're making use of the set of non-accumulation points, which is a relatively new concept that Asaf introduced a number of years ago, and in his paper on the Ostashevsky square, and there's some explanation there. But it seems that until then, there's sort of this lost gem of nobody has ever looked, or people haven't been looking at. People focus on the accumulation points of club sets, but have not looked at the non-accumulation points. And it seems that here we will be able to use these non-accumulation points to our advantage. And so the main theorem that we're going to be proving is that from diamond kappa, which if you don't remember what it is, I'll remind you shortly, and box times minus kappa, which is the one we just presented, these two axioms together will imply the existence of a kappa Souslin-tree for any regular uncountable cardinal. It doesn't matter whether it's a successor of regular, a successor of singular, or inaccessible. We can do it uniformly for all of them. So before we actually get to the proof and the actual construction, let's just do some notational questions and deal with some questions about what our trees will look like in terms of notation. Classically, it's common to build a tree out of ordinals, so to speak. You take your set of ordinals up to kappa and then decide what the order will be on that set of ordinals. We find it easier to do something a little bit different. What will our trees look like? Instead of a collection of ordinals, it's a downward closed subtree of binary functions. So, do a bit of a quick thing. So instead of, we've got whatever our tree is going to end up being, instead of the points being sort of ordinals in some, where the order needs to be decided, we'll have, functions from alpha to kappa here, and this at level alpha, and functions from beta to kappa at level beta, and so on, where being an extension in the tree simply means an extension of the function. So, yes, thanks. You can make it wider if you want, but there's no reason not to make it binary at this point. So yes, thank you. And so yes, the nodes. So the tree will be a normal downward closed subtree of less than kappa of functions from less than kappa to 2. Each node is a function. Tree order is this extension of functions. Restriction of functions is restriction in the tree. So the height in the tree is the domain of the function. That the predecessors of T is all of some node T is all of its restrictions to smaller ordinals, and the level is the level of the alphth level of the tree is the collection of functions from alpha to 2 that are in the tree. One of the advantages of doing this is the ease of completing a branch. So if we've built at some point, suppose we built the tree up to alpha and haven't yet built level alpha, so we've got a bunch of nodes here. We want to decide what nodes to put at level alpha. Well, we can talk about a collection of nodes leading up to here and simply say, take their union and put that node in the tree if we choose to do so. All right, this is a reminder of Jensen's diamond principle. The existence of a sequence. The idea is guessing things. So we've got a bunch of, anything of size collection of things well, in this case, in Jensen's case, the idea was we were talking about guessing collections of ordinals up to kappa, of course, right, so we formulate a sequence Z beta for beta up to kappa. Of course, it's kappa many items, which is fewer than the total number of subsets, and so the axiom is that we can guess them by their initial segments. The question is that, especially since we're building our tree not out of ordinals, but out of functions, we want to guess things that are not necessarily subsets of ordinals. And so this leads us to formulate a slightly different guessing principle that allows us to guess arbitrary objects of size kappa. So we've got our axiom, principle here, diamond minus of h kappa, asserts the existence of a sequence of z beta, still for beta going up to kappa. In this case, the z betas are not sets of ordinals, but sets of arbitrary items, essentially, out of h kappa. The point being they will allow us to guess, using an elementary submodel, any item in h kappa, any subset of h kappa can be guessed by a submodel using this collection of sequences here. So it again asserts the existence of a sequence z beta for beta up to kappa, so that for every p, because you can always start with sort of a p to include in a submodel, for every p in h kappa plus, and every subset of h kappa, there's an elementary submodel that will contain the given p, and that will sort of intersect the set of ordinals at a particular ordinal, and then that ordinal will determine what guess. Is there a pointer button? How does it work here? This one, right? Yeah, I'm sorry, okay. The model will intersect kappa at an ordinal less than kappa, and the point is then, the z in particular, we're guessing at the right time, the z of that ordinal will be the intersection of the model with the set we want to guess, the set z that we want to guess. Well, it's just saying that whenever you build an elementary submodel, you can always include something in it. So it's just a way of saying we can make sure our model contains the things that we want it to have. That we will need to talk about when we use the model to prove something. And correct. That's the point here. That's the difference between Jensen's original formulation and this one. Z is any subset of h kappa. So this is again. So the m intersect kappa is an ordinal. That's what we mean here. M intersect kappa will have to be some ordinal less than kappa. So that allows us to use it as an index because z is indexed by the z betas are indexed by the ordinals. So m intersect kappa is an ordinal, but z beta is simply a subset of h kappa. Which we're hoping will be, z beta, well, the point is therefore it will have to be a subset of h kappa, and we're hoping that it will be the right one, we're claiming that it will be the right one to capture the portion of z that is inside the model. So this kind of formulation will be easier for us to use when guessing, when building objects and guessing objects in the course of building a tree. And the important thing about it is that it's equivalent to the original. So anytime we prove an axiom from Diamond, we might as well just use this version of Diamond. Sorry, if we prove a theorem from the axiom of Diamond, we will use this version. And I'll show you in the course of the proof how it gets used. What do we have next? All right, so we're going to start on building the tree. Preliminary, so we fix our diamond minus h kappa sequence as we've just been talking about. We fix a C alpha sequence witnessing our new axiom that we mentioned before. And we fix an arbitrary well ordering. The purpose of fixing well ordering is to be able to identify a least element, well, we'll see as we go along, just so we can have a definite least element to choose at some point. So our arbitrary well ordering on h kappa. So we want to build a tree. The easy part is to start with the root. That doesn't take too much effort. And successor stage is equally easy. We just split at every node, make sure our tree is splitting, and it's binary, and that's about it. So let's move to the interesting part. What do we do at limit levels? So fix a limit level alpha. Suppose we've built our tree, we've built all the levels of our tree below alpha. We need to decide which branches through the tree up to alpha will have their limits placed in the level alpha of the tree. And we need to make sure there are enough nodes there so that the tree is normal, and meaning to say every node that is already in the tree below alpha needs to have some node above it placed into the tree. So we're going to call that B alpha x. And the node will be the limit of some sequence starting with x. But we have to be careful, because the point of doing this, the point of not just including everything, is we want to be sure that we can kill all potential anti-chains. So this needs to be done with some attention. The question is, how are we going to do it here? So we want to identify some cofinal branches. So if you remember that C alpha was a club subset of alpha, so we're at a level alpha. So let's actually start with a bit of a picture here and then see where we can go. Should I just go back in case that's helpful here? Okay, we've built our tree up to level alpha. Here's alpha. We've got some node x. We need to put some, and there are many sort of potential branches up here. We need to put some node at level alpha into the tree above x. Question is, how do we choose it? So we're going to build a chain in the tree going up to level alpha. And we're going to choose this chain carefully, and then take its limit and put that into level alpha of the tree. All right. So recall that C alpha, we have our club C alpha, so we can fix a number of, we have our sequence of ordinals C alpha that takes us up to alpha. So we're gonna start with x's in whose height is in C alpha, and then we're going to build a chain with levels at each ordinal going up to alpha. Okay, so the idea is we want to have an increasing continuous sequence of nodes. The domain will be the ordinals going up to alpha in C alpha in particular. Start with x itself, and we need to identify what to do both at successor ordinals and at limit ordinals to get all the way up to the top here, to where we want to go. All right. So what do we do with the successor ordinals? The idea is here. So supposing we've built our chain, suppose the x is down here. I really should have more room here. Okay. So our x is down here, and suppose we're building our chain up to here, and suppose we've decided what we will do at level. Suppose we're up to level. Suppose we're up to level beta. We want to know where to go here, but the last point that we've put in is at the point that we're going to call beta minus. The height we're going to call beta minus. So we've got two consecutive ordinals here. There's a beta and a beta minus. We want to go, we have our point decided here, and there are possibly many choices of successor, in a sense, points at the next level that we need to put into the chain. So what do we do? So the question is, we're going to advise with the guess, the Z beta. So Z beta, a priori, is some arbitrary subset of H kappa. But supposing Z beta happens to be some sort of a maximal anti-chain in the tree up to beta. And so if that is, Z beta is a maximal anti-chain, then what that means is that our point at height beta minus is compatible with something in that maximal anti-chain, and we can take the combination of the two and extend it up to some point in at level beta. There may be many such choices, but we can choose the least one, and this is where the well ordering is important. We want to have a definite choice, and so that's what we do. Again, if Z beta is such that we can have this compatibility condition, meaning to say that there's something in Z beta that is compatible with our previous choice, and we can extend it to something at the level of beta, then we choose the least such thing in the well ordering so that we have one. If that can't be done, because remember, Z beta was arbitrary, so there's no reason to assume it should be possible. If it can't be done, then we simply extend it a priori arbitrarily, but we do it according to a well-ordering so that we have a definite choice. We simply say whatever our point was, take the choice in at the beta level that is guaranteed by that is the least in the well-ordering. But there must be something there because we're always building our tree to be normal. So there necessarily is some point at the level beta in the tree above the point at beta minus where we were at before. And so as I was saying again, if Z beta is a maximal anti-chain through the tree up to that point, through the tree below beta, then there is something compatible with the thing we've chosen, and so their common extension is in the tree, and then we can find something above it by normality to put there. If not, we just do the arbitrary, essentially arbitrary, but chosen by a well-ordering point in the higher at the beta level. Okay, so that says what we do at the non-accumulation points. Now, what are we going to do at the accumulation points? Well, we want our chain to be continuous. So at accumulation points, you have to do only one thing. There's only one thing you can do. But the question is it possible? Because again, what are we saying? We're making sure to identify a chain through the tree already constructed. If we're at some limit level, and we've got a chain going up to there so far, how do we know that the point we want, that limit point, is already in the tree? We've built the tree up to alpha. We're trying now to identify a chain through the tree up to alpha, and we're at some limit level beta. So, a priori, we might get stuck. And so again, we want it to be continuous. The only possible definition is taking the union, and that is at the right level, but how do we know it's in the tree? We might get stuck. So this question actually highlights the difference between the classical methods and our method, because in the classical method, it is precisely this, with Jensen's tree construction, it is precisely this question that imposes limitations on what kind of axioms you had to have started with in order to get a Souslin-tree. You have to make sure that at a level that could be such a limit point, where we want to take a limit of a sequence, we have to make sure that was never a point where we were trying to kill anti-chains. Because if we were trying to kill anti-chains here, there are many points we would not have inserted into the tree in the classical method, and then we can't necessarily expect the point we want to be there always to be there. But the way we're doing it is slightly different, and because the basic idea is that because we're not using the accumulation points to kill the anti-chains, rather we already killed the anti-chains at the non-accumulation points, so essentially the node that we want to be there always will be, and let's see why. Essentially, so since we're at an accumulation point of C alpha, so our C beta also was the same sequence up to here. So if C alpha was this sequence, sorry, that's the wrong level. It's beta is here, I guess now, right? So we've got our C beta, which goes up to here, the same thing as the C alpha intersected with beta. And the point is that, for example, for this same point x that we started with, when we were building the tree at level beta, we built a sequence going up to beta and put that point in C beta. And it is that very same sequence that we've followed to build the sequence up to alpha. So because we've chosen the nodes at each point according to a particular rule, which was kill anti-chains if we can, or if not, take an arbitrary point, but it's well chosen in the sense that it's the least according to a well-ordering, we're following the same rule at every stage to choose the next point, to choose every point, whether it's going through up to C beta or going up to C alpha, meaning the B. So let's look at it here. So for every gamma below level beta in the domain, so the value of the B beta x for gamma was determined in exactly the same way as the B alpha x for gamma. So we started at the same point. At the non-accumulation points, we depended only on the potential anti-chain and the things before it and the tree up to that point. And we're always taking limits at the accumulation point. And finally, we would always put that limit into the tree. So we always would have put that limit into the tree at level beta. And so the tree at level beta has already been constructed. The construction guarantees that we've included that limit of that sequence into T beta. And that is exactly the point that we need to continue our sequence going up to alpha at level beta. So this is an important step, an important sort of strategy or important result of using our different axiom that makes it easier to pursue this construction without having to worry about, exactly what stationary sets are involved to begin with. And so we've managed to build our sequence B alpha x going up to alpha, so it's going up to the level alpha. So what do we have? The sequence B alpha x just identified determines a cofinal branch containing x. And then, so as promised, we take its limit, which is something at the right height, and we put that in, and we're going to put that into the tree. So we define the boldface B to be the limit of that sequence going up to alpha, and then we put all such things into the level alpha, and that is our level T alpha of the tree. All right. Having constructed, then of course we take the tree as the union of all the levels we've constructed. So what do we need to do? We need to show that the tree is Souslin, of course. That'll be our next step. Before that, let's just do a little claim in order to show how, which will be necessary, but it'll also display how we use our axiom. So what do we need here? So suppose we have a maximal antichain. So again, the idea will be we want to show that there are no maximal antichain, no antichains that are too large in the tree. So suppose A is a maximal antichain, then we've got this set, which is a stationary subset of kappa. That's the claim. What's the idea? Well, that this set is, the idea being that we want Z beta to be guessing our set up to level beta of the tree, and that it should be a maximal antichain, so that in some sense, well, we can use it later, but yeah. Meaning, say the idea should be that the level beta reflects the property of A being a maximal antichain in the tree in the first place. What is the proof? Well, to show that something is stationary, we're going to take an arbitrary club and show that it intersects the stationary set. So let P be all the things that we want to be able to talk about in our potential elementary submodel. And using the fact that we had our diamond minus H kappa axiom, meaning we had our sequence satisfying that property, we can pick an elementary submodel containing P, with the right ordinal that intersects kappa in an ordinal, and that at that ordinal, the Z beta of that correct ordinal will be the antichain intersecting the model. That's what we said that our property diamond can give us. So D is a club subset in the model, so the supremum of ordinals in the model will be in D. That's the beta. We claim, so we want beta to be in our set B. That'll give us the result we need. So for everything less than beta, we've got everything we need. The alphas are, so it's but by elementarity, essentially the alpha, all the levels less than beta will be included in the model. So essentially, the model correctly reflects the tree down to the right height, and because Z beta was the guess of A, that gives us, the Z beta is the right guess of essentially of this antichain below the tree, and then of course by elementarity the correct properties reflect, so Z beta is also a maximal antichain. This sort of usual elementarity arguments involving trees is what that is. What do we do with that? We are going to use that to prove the tree is a Souslin-tree, a kappa Souslin-tree. So start with an arbitrary antichain. We want to show that it's not too big. From the previous claim, we've just said that set B is stationary. So now we apply our principle, box times minus principle. What is the idea here? That we obtain a limit ordinal giving us the right intersection that we need. What are we saying here? Essentially, we've got our tree, all right, a possible maximal anti-chain through the tree. We use our axiom to give us an alpha, so the soup, so that the points in this, so the points of the C alpha will intersect this set B that we've just defined. Very often, in particular, the non-accumulation points of C alpha will intersect B. And so what that means is that we can pick, what do we want to do with the maximal antichain? In order to show that it's small, we want to show that in particular it can't extend beyond alpha. All right. So if there's any point up here that's potentially in the maximal antichain, well, any point up here we know extends something at the level alpha. Okay. If we can show that any point at alpha was compatible with something in the antichain below alpha, then this and certainly this could not have been in the antichain to begin with. So how do we do that? Classically, antichains would have been sealed at the level alpha. We have to go down to the level beta below alpha, and that's how we're using the axiom here. So basically, we consider our point that was put in here at the alpha level. We say, well, how was it put there? All of these points were constructed from some x as a limit of some chain that had begun from some x below here. So we fix the particular x, and then we say, all right, there's our sort of sequence b alpha x going up from x up to this point v up here at level alpha. All right, and we say, well, what happens to it? Well, if we know that we can find some point above x that's in some point above the height of x that's in both the NAC of C alpha and in B. So we'll choose it a height. What did we call it here? Beta, right? Yes. All right. So we fix a height beta. Well, what happens at beta? Because it's in B, so we know Z beta was the maximal antichain in the tree up to here. Well, if that's the case, then when we built this chain going up to height alpha, we explicitly made sure that the point here would be compatible with something in that maximal antichain. So we've got that going through here. Well, that means to say that, and this Z beta is the initial segment of our A antichain. So what we've really shown is that the antichain actually had a point here, and essentially that's what we have. That is the point that's compatible with our V up here, and therefore the V and anything above it cannot be in the maximal antichain. So we've shown that our maximal antichain is bounded below level alpha in the tree, and of course the width of the tree is less than kappa at every level, so the antichain itself cannot have size kappa. Did I do that a bit too fast? Does anybody want to ask anything to clarify? All right. Okay. So that more or less, actually that does complete the proof that T is a Souslin-tree, Kappa Souslin-tree. Okay. So now let's see what questions. So how does this fit with the other axioms? We've built a tree from our new axiom. How does that relate to the other axioms? Essentially, from most of the common classical axioms that build a Souslin-tree, that can be used to build a Souslin-tree, do imply our axiom, and in fact even a slightly stronger version. I've left out the minus here. I haven't told you what box times means without the minus. I'll get to that a bit later. It's something slightly stronger. So the point is, it certainly implies the version that we just used to build the tree. And all of these sort of classical axioms that have been used to build Souslin trees do imply our axiom. So it makes sense to funnel those constructions, or to funnel construction of a Souslin tree from those axioms through the new box times minus axiom, new box times axiom. And again, so the classical ones involving diamond, involving square and CH, involving the square with built-in diamond for that has been worked on, and some other situations of a subcompact with an extender model, and in the case of V equals L for arbitrary, including inaccessible cardinals, which beforehand was hard to sort of do from axioms, now can be done through this axiom as well. And here's a model in a co-enforcing extension, which also gives our axiom and therefore gives the Souslin-tree, and the result being that we get a kappa Souslin-tree uniformly in all these scenarios. It's the same construction, don't need a different construction of the tree for any of those scenarios, meaning it doesn't depend on the axioms, doesn't depend on the construction, doesn't depend on exactly which of those axioms you're starting from, doesn't depend on whether kappa, as I said before, is inaccessible or successor of regular, successor of singular. It all funnels through this, it all goes through the same construction. Yes? Almost. The only ones that maybe don't will imply a slightly weaker version, which I'll mention later, which is also sufficient for the construction. Meaning, there's one or that'll be, okay, sorry. Okay, so that's, let's now say, what can we say about how fast the levels grow in the tree we just built? At every level, we're putting at most one node above everything that's been built before. I say at most because we are putting one for every node before, but it's possible that we put the same node for two things before it. But in principle, so in terms of cardinality, it's at most one for everything that was there before. And so the level of each tree is always bounded by the height of the tree, with the exception of finite levels where you might grow fast at finite levels. But we're always the width of a tree is never bigger than the cardinality of its height. So we call such a tree slim. And that is how the tree we've just built looks. What if we want something different? What if something opposite like complete? Sometimes we want our trees to look a bit more like forcing partial orders, in which case we might want some level of completeness, some degree of completeness. So a tree is chi complete if every increasing sequence from the tree of length less than chi has an upper bound in the tree. Now, if we want to complete the tree, we can't exactly do what we did before. What can we do? To get our tree to be complete, we would like to tweak our construction so that we can put, so that at levels of small enough cofinality, we put all branches up to that level into the tree. Will this work, or will it break everything we've just been talking about? Well, for one thing, we need some bound on the cardinality, on cardinal arithmetic. Otherwise, the tree will get too wide. So we have to assume that that there aren't too many branches leading to a level alpha. Otherwise, it generally cannot work. But so that's one assumption. But even still, if instead of doing this careful choice of things at alpha, we just put everything into level alpha, we run the risk of losing the possibility of killing antichains when we choose alpha there. How do we kill the antichains using the C alpha? So we need to tweak the axiom to avoid such levels. So question is, how are we going to tweak the axiom? So we've used in the construction we just did, we used a diamond and box times minus. So we want to say something about making sure, strengthen one of those axioms. Which one should we strengthen? Well, classically, the construction of Souslin-trees when there was an attempt to build a Kappa-complete, a chi-complete Souslin-tree, they would replace diamond with diamond of Kappa with diamond on a subset, so that you could focus on things with large enough cofinality. We need to do something like that because we want to be able to focus our guesses, focus the places where these guesses take place on large enough cofinality, on heights alpha that are not where we are completing the tree, but rather where we are carefully guessing nodes in the tree. And so it turns out that rather than changing diamond to do that, we're going to change our box times minus axiom to do that. So here's the previous version that we had before. This is just this this is just a repeat of what was defined before, the principal box minus kappa. But notice the highlighted sections, and those are going to change. We now have box minus S for an arbitrary stationary set S, where instead of the principal giving us an arbitrary ordinal or arbitrary ordinals in kappa, it gives us ordinals that have to be in the given set S. So if we state our axiom with the set S that we want, namely sets of large enough cofinality, then we can make sure that the guessing alpha here will take place on sets of large cofinality, and then we can choose to complete the tree at levels of small cofinality and not get in the way of our guessing that needs to happen. And so the theorem is that if you have a regular uncountable cardinal and any chi below it, satisfying that arithmetic hypothesis that we've decided we were going to need, and then this strengthening of box times minus involving this, that means the sets of, the ordinals below kappa of cofinality at least chi, that will imply the existence of a chi-complete kappa Souslin-tree. And one thing to notice in terms of an advantage of this approach, can everyone see the bottom of there, is that the advantage of doing it this way is that we can get models or situations where we do have diamond and this strengthened box times minus, but you wouldn't have gotten a strengthened diamond. So there's already another advantage to our approach here. Okay, so let's now talk about how to remove that minus sign from the box times minus. Okay. So this is what was on the board before. This is still the box times minus. Remember that we're talking about being given a cofinal subset, and we want to talk about guessing something from it. Well, what if we're given not just one, but a sequence of cofinal subsets that we want to make sure we can intersect carefully? So this is now a stronger version of the axiom that for any sequence of cofinal subsets, every one of those will intersect the non-accumulation points sufficiently often. And we're going to do one more strengthening, which I'll mention here, and that is, I'm not quite going to define all the terms here, but instead of saying just that our chain has, that our sequence C alpha has many intersection points with the set B or Bi that's given, we want to say that it has many sort of blocks of intersections. So as we go up, we want to have sort of a set of consecutive points from C alpha that are all inside beta, omega consecutive points. And the farther up we go, we want to make sure that there are unboundedly many such blocks rather than single points that are in the non-accumulation points of C alpha that are also inside the given cofinal set Bi. So that simply means the next omega many elements from C alpha above, I think that was supposed to be minus beta, above beta. I think we left something out here. That was above should say above beta. You know, like otherwise you're quantifying over an ordinal that doesn't appear. All right, so we're quantifying over beta. Beta should appear here. It's C alpha minus beta, so that should be replaced with C alpha above beta. And the idea is that we want to have many betas so that from beta you take the next omega many things in C alpha, and those will be inside the set Bi. Okay. All right. So if that wasn't complicated enough, that was actually a special case of a parametrized proxy principle, which we've defined with something like eight parameters. All right, I'm not going to give a definition here. But why all these parameters? So the idea is that by tweaking all these parameters, we can control the properties that the Souslin-tree satisfies. again, focusing on the idea that the constructions are in some sense uniform. We know already, we've seen now, how to build this Souslin-tree. And if we start with a slightly different version of the axiom, namely by tweaking these parameters, we can get something slightly different in the outcome. And so let's give an example here. So using some version of the axiom with these eight parameters, we get this theorem. So from square with built-in diamond and GCH, you can get an Aleph 7 Souslin-tree and a sequence of uniform ultrafilters, so that the reduced ultra power of the tree, essentially taking the reduced ultra power by that ultrafilter, will either give an Ehrenstein tree or give a non-Ehrenstein tree, depending on exactly which n we're using. So we have a lot of control using we can build a Souslin tree with a lot of control over exactly what happens to it and what it looks like in terms of reduced powers, using particular values of the parameters. Yeah. That's what it should be. It's just what it should say, I think, right? Yeah. And just for some fun, I mean, of course, there's nothing really special about 7 here, but if we move it down to 6, we can fiddle with the numbers to make sure that all the prime numbers are in one set and all the non-prime numbers are in the other set. So that makes for a cute formulation. Anyway. Okay. Another example. We know that there's a classical proof that, or Baumgartner, Melius, and Reinhardt proved in 1970, that in a 1970 paper, that every Aleph 1 Ehrenstein tree can be made special. There's a specializing forcing that was can be made special in some cofinality preserving in a CCC extension, which is therefore cofinality preserving. So the question is, what happens with that? Is anything parallel at higher cardinals? Well, in fact, what we can show is we can talk about getting a lambda plus Souslin tree that cannot be specialized without reducing it all the way down to Aleph 1, essentially. So certainly can't be specialized with a cofinality preserving extension. And in fact, the only way to specialize it is to collapse its cardinality down to Aleph 1. So again, with this is the theorem here, supposing square and CH with lambda for a singular cardinal. So we can get a Souslin tree, which is obviously certainly an Ehrenstein, in particular a Souslin tree, satisfying this condition that for any ZFC extension in which the tree becomes special, then we must have collapsed that cardinal lambda down to Aleph 0. So this is just an example of one of many things, the point being that we used the proxy principle in order to derive this, in order to do this construction and derive this result. A couple of other things, I'm not necessarily going to define all the terms here, but assuming this version of the proxy principle with these parameters, we can get a coherent Kappa Souslin tree, and assuming another version with different parameters slightly, we can get a free Souslin tree. And then before I just mentioned about a non-specializable tree in the sense that it couldn't be specialized unless you collapse cardinals, well, with a different variety of parameters, variation on the parameters, and assuming GCH, we can get a Souslin tree, a lambda plus Souslin tree that is specializable, meaning to say specializable with an extension that doesn't change the cardinal structure. Preserving cardinals and cofinalities. All right, so now what? Turns out there's more, but what we're going to talk about here is, by tweaking the parameters and varying the construction slightly, this answers Boaz's question slightly earlier, we can construct a Souslin tree from slightly weaker axioms than the ones we mentioned before. And so the point here is there's a form of the proxy principle that is true with certain parameters that allows the construction of a Souslin tree for uncountable lambda, assuming any one of the following. And these are sort of classical axioms from which Souslin trees have been built. You can see this as an extension of the list from before. This is the one that Jensen used, and these are other sort of Cohen extensions, Prickery extension, where you can get a a Souslin-tree. This was from Gregory, I think. Is this that right? There's one from Gregory. Pardon me? Is new. Sorry. Right. This looks similar to the Cohen, but it's different. And this is a new result we're getting. So because our proxy principle follows from this extension, then we get a Souslin-tree in that case. This one is from Gregory, and we can extend that to the singular case where you can't get this, but rather we can have some still GCH and some weak version of square and CH, and that will be enough to get us a version of our principle, which can therefore lead to constructing a Souslin-tree. Is there something else on this slide? All right. What? Sorry? Was there? All right. So far it seems that all the axioms we've been talking about seem to be focusing on things like, well, we mentioned V equals L and all these sorts of square axioms and related axioms that seem to be true in V equals L. Is there any relevance to our approach if we don't like working in V equals L? And the answer is yes, we can actually get a model of Martin's maximum. So what are we doing here? Assuming supercompact cardinal, which you would always need to get Martin's maximum, we can get a model that satisfies Martin's maximum and two versions of the different parameters in our principle, which in particular combine to give a free Kappa Souslin-tree for all Kappa greater than all of 2. That turns out to be, in a sense, optimal, because for anything all of 2 or less, you wouldn't be able to get a Souslin-tree because of Martin's maximum. PFA negates the existence of an all of 2 or all of 1 Souslin-tree. Well, certainly all of 1 is negated by MA, and for all of 2 it's negated by PFA, so you can't get a Souslin-tree at those smaller levels. So therefore we've got an optimal result here, that for anything greater than all of 2 we get a free Kappa Souslin-tree in a particular model satisfying MM, Martin's maximum. I guess that's basically it. So if there are any questions, I'll be happy to discuss further. We haven't really gotten into that, so not quite sure. I suspect there's a lot of things we can do if we tweak the parameters a little bit, or possibly introduce a 9th parameter. Never hurts. So I guess I'm not sure at this point. Does you have an idea? This one here, sorry, this prickly thing that's mentioned here. Oh, yeah, we might have to widen the tree. In our original constructions, we actually built all our trees to be wider than, not necessarily binary, but more prolific, more splitting more widely. So yeah, it could, and then so now we just changed that. Yeah. I should have said that initially. I mean, it was kind of arbitrary to insist that the trees we build are binary. It really doesn't matter, even for the default construction. Even for the construction I presented, nothing would change or get ruined if you say that every level, every level should have more ordinals at the successors, more nodes at the successors. Yeah.
Look at the weaker squares, like square couple omega, and where the omega many gets
Right. Yeah.
No, the position for the diamond feature is no problem. tree automatically generates square kappa omega.
Right. I mean, we definitely have a way of getting more. One of the if we tweak this, well, this is okay. Going back to the here general whatever. This says something about how many clubs we're allowing at each level. So in our default construction, we allowed only one. We started with one club. But yes, we can have a weak version allowing more. And that will correspond more to weaker versions of square, I believe.
The issue is, what I'm asking is, I mean, there is a very general, I mean, pre-create introduces square kappa omega.
Yeah.
So, immeasurable. So the issue is, and suppose you got the calculator which allows you to get the diamond kilo, but that automatically gives you, let's say, square in each of the.
Well, that's just wrong, because you see, it's not just one diamond, you also want the sequences.
Yeah.
Yeah, exactly. You want to know that.
No, I know. Yeah. Suppose you got omega many things. But the eating in this case would be there is an alpha, so all the
Yeah, exactly.
all the omega many sequences. So
Yeah.